In this problem, we have a small bullet hits and embeds in a piece of wood hanging from a string. The block of the bullet swing to a position 15 centimeters above the rest position. If the mass of the bullet is 3 grams and the mass of the wood is 0.5 kilograms, what was the speed of the bullet? So when we look at this type of problem, the first thing we notice is that there is a collision. And no matter what type of collision, we know that momentum is conserved. So we want to approach this problem as a conservation of momentum problem. We start with the block and the bullet separate. And the bullet is moving, but the block is stationary. And then afterwards, the bullet embeds in the block of wood, and they move together as one. And so we have the separate in the beginning. We have the mass of the bullet, and we have the mass of the wood. And then separately, we have the velocity of the bullet and the velocity of the wood. Now, we know that the mass of the bullet is 3 grams, and the mass of the wood is 0.5 kilograms. And the problem is that the units don't match up. So in order to do these problems, we have to have the units be the same. Typically, we in physics go to kilograms instead of grams. So we're going to convert from 3 grams to kilograms by dividing by 1,000. Okay, so it's 0.003 kilograms. Now I'm actually going to just erase this here and rewrite it so we don't get confused and accidentally use the wrong mass later on. So we're going to use the kilograms, 0.003 kilograms. We know that the velocity of the wood in the beginning is 0, and we are trying to find the velocity of the bullet. After the collision, they're going to combine together, so I'll use a subscript of t to show that they are together. And the mass when they are together then is 0.503 kilograms. Their combined mass of 0.003 plus 0.5. The problem is we don't know the velocity after the collision either. We're only allowed to have one unknown. So therefore, we somehow have to figure out what is the velocity directly after the collision, and then we can go back and solve for the velocity of the bullet. The only thing extra that we are told is that this whole situation, this whole combination of the bullet and the wood is going to raise up 15 centimeters. Now that is that's going to tell us then that we should use the conservation of energy. Because it is raised up, it is increasing its potential. So therefore, we're going to use conservation of energy for directly after the collision to figure out how fast everything is moving right after the collision takes place. Now, in doing a conservation of energy, we're going to talk about the mass and the speed and the height, both in the beginning and at the end. And for this situation here, we're talking about the beginning being right after the collision, and the final or end is right when it's reached its highest point of 15 centimeters. Now the mass in the beginning is 0.503 kilograms. It is both the bullet and the wood combined. And at the end, they're still combined, so the mass is still 0.503 kilograms. We're trying to find this speed right after the collision. That is our initial. We know that the speed at the end, when it's reached its maximum height, is 0 meters per second. Our initial height is 0 meters because it starts at the bottom, and then the final height is 15 centimeters. But we're going to have to convert that to meters. So to convert from centimeters to meters, we divide by 100, and we get the final height to be 0.15 meters. And so now this is a conservation of energy, which says that the kinetic plus the potential in the beginning is equal to the kinetic plus the potential at the end. We have our potential energy, which is m times g times h in the beginning, and our kinetic, which is 1/2 mv squared in the beginning, is equal to the potential, which is m times g times h at the end, plus 1/2 m times v squared at the end. At this point, we can place in our values. We have that our mass is 0.503. We have that g is 9.81, and our height is 0 in the beginning. Again, the mass is 0.503. We don't know that initial speed. That's what we're trying to find. Again, mass is 0.503. G is 9.81, and our height is 0.15 at the end. And then we have 1/2 of 0.503 times 0 squared. Now again, what I would recommend is solving for these terms here, like 0.503 times 9.81 times 0 is 0. Here we have 1/2 of 0.503, and that is 0.2515 times vi squared. We have 0.503 times 9.81 times 0.15. Which is 0.74. And then we have 1/2 of 0.503 times 0 squared, which is 0. Now in this situation, again, we can really ignore the zeros, so we can just kind of erase that, because they go away. And this is a much easier problem then to solve for our initial speed. When we solve for the initial speed, we solve for that speed to be 1.72 meters per second. Now this is the speed directly after the collision. So now what we do is we go back to that previous part, and that is our speed after the collision, after they have combined together, after the bullet has embedded in the wood. So this now is 1.72 meters per second from what we just found. And now we're going to use our conservation of momentum, which says that the m times v of all the objects in the beginning, or the total momentum in the beginning, is equal to our m times v of all the objects at the end. There's only one object at the end. Now we can place our values in. We have the mass of the bullet as 0.003 times the velocity of the bullet, which we don't know, plus 0.5 times 0 is equal to 0.503 times our value we just saw for 1.72. And so this here is just the 0.003 times v plus 0. See, this kind of goes away. And we're left with 0.003 times the velocity of the bullet before the collision. And we have that this value here comes out to be 0.865. We then divide each side by our 0.003. And we get that the velocity of the bullet is 288 meters per second. So again, we use the conservation of energy in order to get the velocity after the collision. And then we use a conservation of momentum to get the velocity of the bullet before the collision.